Welcome to online lecture series in organic chemistry, and we are discussing the important chapter, that is stability of metal complexes. In earlier video we have seen the factors affecting thermodynamic stability of complex, and we are discussing about the nature of central metal ion. So next important term, that is the crystal field effects. Crystal field effects decides the stability of coordination compound or metal complexes. Now, as you know that in periodic table from left to right, the ionic size decreases, especially in 3D series, that is from scandium 2 plus to Zn 2 plus, ionic size gradually decreases, and reason for this is in a given particular row the number of shells remains constant and electrons are progressively added in the same shell, and number of protons in the nucleus increases and number of electrons progressively increases in the same shell, and therefore the force of attraction between protons and outermost electron gradually increases, and thereby the shell becomes compact, and hence the size, atomic as well as ionic size, gradually decreases from left to right in periodic table. So here we are considering the metals from calcium to zinc, especially their dipositive ions. So from calcium 2 plus with electronic configuration D0 to Zn 2 plus with electronic configuration D10, from calcium 2 plus to Zn 2 plus, ionic size gradually decreases. Now consider these ions, they are forming the aqua complexes. M2 plus when combines with 6H2O, that is water ligands, and then there is a formation of MH2O6 hexaquo metal complexes where metal is calcium to Zn. Now the formation of this aqua complex for calcium to Zn, their stabilities especially changes from calcium to Zn, and in earlier video we have seen that the stability of complex depends upon size of metal ion. Smaller the size, greater is the stability of complex. Stability and size, there is an inverse proportion that we have seen in earlier video. Now here when we plot log K versus these various metal ions, especially size, from calcium to Zn 2 plus, the ionic size gradually decreases, and as the size decreases, the log K values of aqua complexes of these ions, that is calcium, scandium, titanium, vanadium, chromium, manganese, ferrous, cobalt, nickel, copper, zinc, the stability of aqua complexes of these ions gradually and linearly expected to increase. So from calcium to Zn 2 plus, the stability of hexaquo complexes are expected to linearly increase. So this is the expected increase, or this dotted line indicates the expected increase. So log K values of MH2O6 2 plus are expected to increase from calcium 2 plus to Zn 2 plus, but the experimental log K values shows double hump curve with the maxima at vanadium 2 plus and nickel 2 plus. So experimental log K values are different. Expected or experimental log K values are little bit different than the expected. Now here one by one we can see. So for calcium 2 plus, its configuration is D0 and crystal field stabilization energy is 0. It is observed that as the crystal field stabilization energy increases, the log K value also increases. So it is directly proportional to crystal field stabilization energy. For calcium 2 plus, as crystal field stabilization energy is 0, its expected and observed log K value is same. There is no change. Now consider the scandium 2 plus. For scandium 2 plus, its configuration is D1 and crystal field stabilization energy is minus 4 dq, and its experimental log K value is greater than the expected. Similarly, for titanium 2 plus, configuration is D2, its crystal field stabilization energy is minus 8 dq. There is an increase in crystal field stabilization energy, log K value increases. For vanadium 2 plus, configuration is D3, its crystal field stabilization energy is minus 12 dq, its highest one, and therefore the log K value for vanadium 2 plus, it is highest. For chromium 2 plus, configuration is D4, crystal field stabilization energy is minus 4 dq. Now it is decreased as compared to vanadium 2 plus, and its log K value, it is less than the vanadium 2 plus. For chromium 2 plus aqua complex, the log K value is less as compared to vanadium 2 plus. And for manganese 2 plus, its configuration is D5, and the crystal field stabilization energy is 0 dq again, and as crystal field stabilization energy is 0, its log K value for aqua complex, it is same as expected. It appears on this dotted line. Now consider the Fe2 plus, its configuration is D6, and crystal field stabilization energy is minus 4 dq plus P. P stands for pairing energy. So as crystal field stabilization energy is more than this 0, so its log K value is increases. This is for cobalt 2 plus, configuration is D7, crystal field stabilization energy is minus 8 dq plus 2 pairing energy, that is 2p. So as crystal field stabilization energy increases, its log K value increases. For nickel 2 plus with configuration D8, crystal field stabilization energy is minus 12 dq and minus 12 dq plus 3p, and therefore its log K value is highest. And for copper 2 plus, configuration is D9 with crystal field stabilization energy equal to minus 6 dq plus 4p. It is less than the nickel, and therefore log K value also decreases as compared to, or also less as compared to the log K value of nickel. For Zn2 plus with configuration D10, its crystal field stabilization energy is 0 dq plus 5p, and as it is 0 dq, there is no effect on the stability constant. The expected and experimental stability constant or log K value for Zn2 plus is also same. So remember, actually from this plot, double hump curve, some of the important highlighting points are the high values of stability constants than the expected are due to the crystal field effects and can be explained on the basis of crystal field stabilization energy. And greater the crystal field stabilization energy, greater is the value of K, log K. And for calcium 2 plus, manganese 2 plus and Zn2 plus, crystal field stabilization energy is 0, hence stability constant is as per expected, that is expected value of log K and observed value of log K or experimental value of log K are same. And the vanadium 2 plus and nickel 2 plus shows the highest log K values. So this is about the crystal field effects on the stability constants. Now next important factor we are going to discuss, that is the nature of ligands or coordinating groups. Now the nature of ligand, that is whether it is strongly basic or not able to donate pair of electron, depending upon basicity of ligand, the stability constant values of that metal complex varies. Now higher the basic strength of ligand, greater is the tendency of ligand to form the stable metal complexes. For example, you can see in halogens, fluoride forms more stable complex than the chloride, bromide or iodide. Similarly, NH3, it is better ligand as compared to water, because electron donation ability of amine, that is nitrogen, contain pair of electron. It is able to donate pair of electrons. So amine is better ligand, or it is more basic than water, and therefore amine, it forms the stable complex as compared to water. The stability of complexes increases with pi bonding capacity of the ligands. For example, in this table you can see cyanide and carbonyl. These ligands are able to form the pi bonds and they form the stable complexes. Even stability of metal complexes with thiocyanate ions increases with increase in concentration of thiocyanate. So concentration of ligand also decides the stability constant, value of stability constant. And here you can see, when the blue colored cobalt complex with thiocyanate ligand, to this complex when water is added, then as concentration of water increases as compared to the concentration of thiocyanate, slowly this water displaces or replaces thiocyanate and we get aqua complex, and color of this complex changes to pink. Hexaco cobalt 2 complex, it is pink colored. So as the concentration of thiocyanate decreases or concentration of water increases, then the thiocyanate complex becomes the aqua complex. Similarly, actually this is the reversible reaction. When concentration of thiocyanate is increased, when more thiocyanate ligands are added, then by reverse reaction we get thiocyanate complex and pink color solution becomes blue. Again, when water is added, the solution becomes pink, and when thiocyanate ligands are added, solution becomes blue. It means concentration of ligand also plays important role in the stability of complexes. Another example is iron or ferric ion forms the complex with thiocyanate ion and its color is reddish brown. When this complex, the fluoride ions are added to the solution of this complex, and as the concentration of fluoride ion increases, the reddish brown color disappears and we get colorless hexafluoroferrate 3 ion. Again, this is the reversible reaction. As soon as concentration of thiocyanate is increased, then there is a competition between the reaction of thiocyanate and fluoride. As the concentration of thiocyanate is increased, the solution becomes reddish brown. We get thiocyanate complex, and again when concentration of fluoride is increased, we get a solution becomes colorless. So there is a competition between fluoride and thiocyanate for the reaction, and whichever concentration is more, that complex gets formed. And third example is when blue colored hexaco copper 2 ion solution, it is treated with the chloride ion solution, and as the concentration of chloride increases, the blue color changes to yellow, that is tetrachlorocopper cuprate 2 ion, and as water is added to that yellow colored solution, again the solution becomes blue. That is because of the formation of hexaco copper 2 ion. Again there is a competition between chloride and water for the reaction, and when concentration of water is more, then we get blue colored hexaco copper complex, and when concentration of chloride is more, then we get yellow colored tetrachlorocuprate ion. So in this way, nature of ligand also decides the stability of the complex, basic strength, pi bonding capacity, and concentration of ligands. These are the important terms and which decides the stability.